See, next important thing is Galilean transformation equations. What are Galilean transformation equations? You know that anything which happens suddenly in space is called event, where when it has occurred. So an event at any instant in space has different coordinates in a different system of reference. So I am standing here, it is one event. ಇಲ್ಲಿ ಈ ಕಡೆ ಒಂದು ಕೋಆರ್ಡಿನೇಟ್ ಸಿಸ್ಟಮ್ ಐತೆ ಅಂತ ಹೇಳಿ ತಿಳ್ಕೊರಿ, ಈ ಕಡೆ ಒಂದು ಕೋಆರ್ಡಿನೇಟ್ ಸಿಸ್ಟಮ್ ಐತೆ ಅಂತ. ಇದು XY Z ಆಕ್ಸಿಸ್, ಇದು XY Z ಆಕ್ಸಿಸ್ ಹೊಂದೈತಿ. ನಾನು ಪೊಸಿಷನ್ ಮೆಜರ್ಮೆಂಟ್ ಮಾಡ್ತೀನಿ. Whether the coordinates of both the system is same or different now? Definitely it is different. ಈ ಕಡೆ ಫ್ರೇಮ್ ಆಫ್ ರೆಫರೆನ್ಸ್ x ದಿಂದ 2 ಮೀಟರ್ ಇರಬಹುದು. ಈ ಕಡೆ ಫ್ರೇಮ್ ಆಫ್ ರೆಫರೆನ್ಸ್ x ದಿಂದ only 1 ಮೀಟರ್ ಇರಬಹುದು. That means an event at any instant in space has different coordinates in different frames of reference. Then the equation which provides the relationship between the coordinates of the two frames of reference are called transformation equations. Here at point P there is an event. ಈ event na two frames of reference define ಮಾಡ್ತಾರೆ, S and S dash. Then definitely the coordinates are different. Definitely ಈ frame of reference ಅಲ್ಲ ದೂರ ಐತಿ, ಈ frame of reference ಅಲ್ಲ ಸಮೀಪ ಐತಿ, isn't it? An event at any instant in space has different coordinates. That means P x dash ಬೇರೆ ಬರಿ, y dash z dash ಬೇರೆ. Then an equation which provides the relation between coordinate systems of the two frames of reference or coordinates of the two frames of reference is called a Galilean transformation equations. That means x dash ಗೆ ಯಾವ ರಿಲೇಷನ್ ಐತಿ, y dash ಗೆ ಯಾವ ರಿಲೇಷನ್ ಐತಿ, z dash ಗೆ ಯಾವ್ದು ರಿಲೇಷನ್ ಐತಿ ಅನ್ನೋದನ್ನ ಇಕ್ವೇಷನ್ ಕೊಡ್ತಾವ. ಆ ಇಕ್ವೇಷನ್ ಏನಂತ ಹೇಳ್ತಾರೆ? Geridian transformation equations. So consider two frames of reference S and S dash. It has got coordinates x, y, z. So another one is x dash, y dash, z dash. S frame has got center O. S dash has got center O dash. Let both the frames of references are inertial frame of reference. Means Newton's laws of motion holds good. So a frame of reference S is at rest. A frame of reference S dash is moving with uniform velocity V. It is moving with uniform velocity. So assume that there is one clock in frame S. There is another clock in frame S dash. Time shown by the two clocks in two frames of reference is same or different? It must be same. Because time is an absolute quantity. Invariant. Invariable. Let us assume that at time t is equal to t dash is equal to 0 seconds. T is the time coordinate of S frame. T dash is the time coordinates of S dash frame. At the beginning, both O and O dash coincide. That means X coincides with X dash, Y axis coincides with Y dash, Z axis also coincides with Z dash. Then, after some time, the S dash frame moves with uniform velocity along X direction. S dash frame ಯಾವ ಡೈರೆಕ್ಷನ್ ಒಳಗೆ ಮೂವ್ ಆಗ್ತಿದ್ರಿ X direction ಒಳಗೆ ಮೂವ್ ಆಗ್ತಿದೆ with uniform velocity v. After time t seconds it reaches this point. Now X coordinates of this S frame is definitely more than X coordinates of this S dash frame. So at point P, which is greater, this X is greater, because from here to here you have to measure the distance X by this frame S, and this is what your X dash. Now we know that your velocity is equal to distance upon time. From this, so distance is equal to, so V into T. That means this distance covered by this S dash frame in time t seconds is V into T, because it is moving with uniform velocity V. And there is no change in the Y component and Z component, because Y and Y dash are parallel, Z and Z dash are also parallel, but only this S dash has moved along this X axis. Then from the figure it is clear that this X dash is equal to X minus Vt. This X dash is equal to X minus Vt. You call this equation as 1. What about Y dash? Y dash is equal to Y. Z dash is equal to Z. So T dash is equal to T. Why Y dash is equal to Y? This frame does not move along Y direction, and also it does not goes along Z direction. So in other words, Y axis and Z axis are parallel. They are parallel. And these four equations are called as Galilean transformation equations. You know equations again. So it gives a relation between one coordinates and another coordinates, one coordinates and another coordinates. The equation which provides the relation between the coordinates of the two frames of reference are called Galilean transformation equations. I repeat once again. An event at any instant in space has a different coordinates in a different frames of reference. So an event at any instant in space has a different coordinates in different frames of reference. An equation which provides the relationship between the coordinates in the two frames of reference is called as Galilean transformation equation. Let in the figure there are two frames of reference S and S dash. They are inertial frame of reference where Newton's laws holds good. So the frame of reference S is at rest. This S dash is moving with uniform velocity. Uniform velocity V. Let the time shown by the two clocks in the two frame of reference is same because time is absolute quantity. So at time t is equal to t dash is equal to 0 beginning means t is the time coordinates in S frame, t dash is the time coordinate in S dash frame. Both O and O dash coincides. That means X coincides, Y coincides with and Z also coincides. Let this frame of reference S dash moves with a uniform velocity V. After time t seconds, t is equal to t dash seconds, the distance traveled by this S dash frame is given by V into t. There is no movement along Y axis or Z axis, in other words they are parallel. So therefore this distance is V into t. So P is an event. It is in two frames of reference. Now from the figure we can write this as x dash is equal to x minus vt, y dash is equal to y, z dash is equal to z because they are parallel, and t dash is equal to t. The time shown by the two clocks in two frames of reference is same. These four equations provides the relationship between a coordinates of two frames of reference. Hence they are called as Galilean transformation equations. You have to remember this Galilean transformation equation is x dash is equal to x minus vt, y dash is equal to y, z dash is equal to z, and t dash is equal to t. Now next, invariance of length under Galilean transformations. Means Galilean transformation equations ಮಾಡಿದಾಗ length of any object in one frame of reference should be same as the length of the same object in another frame of reference also. That means length ಯಾವ frame of length of an object ಯಾವ frame of reference ದೊಳಗೂನು ಚೇಂಜ್ ಆಗುವುದಿಲ್ಲ ಅನ್ನೋದನ್ನ ನಾವು ಪ್ರೂವ್ ಮಾಡಬೇಕು. Many times it has been asked in the examination See, consider here P1 and P2 are two events separated by some distance delta x along this x direction. P1 and P2 are the two events separated by delta x or some distance along x direction, and that delta x is measured from this S frame of reference, and also it is measured from S dash frame of reference. So for S frame of reference, see, we have for point P1, I can write this coordinates as x1, y1, z1. And for S frame only, for another point P2, I will write it as, so x2, y2, z2. This is what your another way. Then for S dash frame, what I write, x1 dash, y1 dash, z1 dash. This is for P1, and similarly for another point, it is x2 dash, y2 dash, and z2 dash. And along the x-axis, these two are separated by certain distance delta x. Their separation observed in S frame is given by delta x is equal to x2 minus x1. This is observed from S frame. Similarly, the separation observed from what? S dash frame. This I am going to write it as delta x2, delta x dash is equal to, it is x2 dash minus x1 dash. So finally what? This is the measurement made by S frame, and that is the measurement made by S dash frame, moving frame. It is moving with a constant velocity v. Now in the notes I have written that these points are not shown in the figure, but if you want to show them, once again you have to draw this figure. That's all. So in the examination it is not necessary, but you have to understand how these are separated. That's all. Then you know that these are x dash is equal to x minus vt, y dash is equal to y, z dash is equal to z, t dash is equal to t. They are Geridian transformation equations what we have studied. Now we have to apply Galilean transformation equations. You know that your Galilean transformation equation is x dash is equal to x minus vt. X is the coordinates in S frame, x dash is the coordinates in S dash frame, v is the velocity with which this S dash is moving, it is a distance, v into t is a distance. Y dash is equal to y, z dash is equal to z, and t dash is equal to t. Now you write these Galilean transformation equations for an event P1 first, and after that these Galilean transformation equations for P2. Now for P1, now this is S dash frame and S frame. X1 dash x1 dash is equal to, so this is x1 minus vt, x1 dash is equal to x1 minus vt. It is for point P1 I am writing, or for an event P1. And similarly for another end P2, this is x2 dash is equal to, x2 dash is in the second frame, is equal to, it's x2 minus vt. So not necessary to write other things because they are same. And now your x2 dash minus x1 dash, x2 dash minus x1 dash is equal to, it is x2 minus vt minus x1 plus vt, or this is x2 dash minus x1 dash is equal to x2 minus x1. This is what your delta x dash, this is delta x. That means, so if the measurement of the two events is made simultaneously in two frames of reference, then the distance between the two events remains constant. The distance between the two events remains constant means, if you consider one rod and this rod has got length L, its distance in the first frame of reference is delta x, where your P1 and P2 are what? Endpoints. And for the same rod, if you measure from the S dash, so if it is delta x dash which is equal to L, we have shown that this L dash, this is L dash is equal to L. What do you mean by L dash is equal to L? Under Galilean transformation equations, so the length of any object remains constant. It does not change. Means invariance of length under Galilean transformations. What we have shown is, so invariance of length under Galilean transformation equations. Now repeat once again. See here, suppose there are two events. We have to show what delta x dash is equal to delta x. Suppose there are two events P1 and P2. separated by some distance along x-axis, and these two events are observed from frame S and frame S dash. So since there are two events P1 and P2, for S frame at point P1, the coordinates are x1, y1, z1, and for point P2, its coordinates are x2, y2, z. And similarly for another frame S dash, moving frame of reference S dash, this is x1 dash, y1 dash, z1 dash, similarly x2 dash, y2 dash, z2 dash. Since the events are separated along x direction, so the separation observed in S frame is x2 minus x1 delta x. Similarly, let delta x dash is the separation observed between two events in another frame of reference. Now we know that Galilean transformation equations, because there is a separation along x-axis, the relation between the coordinates is x dash is equal to x minus bt. X dash is the x coordinates in S dash frame. X is the x coordinates in S frame. Now in S dash frame is x1 dash, and this is x1 is in S frame. So therefore x1 dash is equal to x1 minus bt, and similarly this is point P1 or event P1. Similarly for an event P2, x2 dash is equal to x2 minus bt. Therefore this difference, we have assumed that x2 minus x1 is delta x, and also this x2 dash minus x1 dash is delta x dash, and finally what we have to prove is delta x should be equal to delta x dash. Then this is x2 dash minus x1 dash. From these two equations we have proved that x2 minus x1, therefore delta x dash is equal to delta x. So consider, if there is a certain rod of length L is measured by the frame S, and in this sphere we have taken it as delta x, and if its length is measured as L dash in S dash frame, then finally we have shown that L dash is equal to L. What it means? Under Geridian transformation equations, length of an object does not change. Length of the object remains constant. This is what invariance of the length under Galilean transformations. See, next we have to study Galilean velocity transformations, how velocity can be transferred, and also the acceleration is transferred. So this is just transformation of coordinates. So if you differentiate these equations with respect to t, you know that differentiation of first equation is, it is dx dash upon dt is equal to, it is dx upon dt minus v, it is distance divided by time, rate of change of distance, it is nothing but velocity. Distance upon time is velocity. So I represent it as ux dash is equal to, this is just ux minus v. This is the velocity transformation. And similarly the differentiation of another one. So you may write it as uy dash is equal to uy, where u stands for velocity, then it is uz dash is equal to uz. These are Galilean velocity transformations. And you know that the rate of change of velocity is acceleration. Rate of change of velocity is acceleration, means once again you differentiate this. It is du upon dt. Differentiating once again this with respect to the time, this becomes ax dash is equal to ax. This is ax is equal to a dash x is equal to ax. This is 0. Then this is what? A y dash is equal to ay. Az dash is equal to az. And these are Galilean acceleration transformations. So what I've done, I think these are the Galilean transformation equations. First, the differentiation with respect to time will give the velocity, and again if you differentiate them, you will going to get what? Acceleration. So what do you mean by that ax dash is equal to ax? Means acceleration of a body in one frame of reference is equal to acceleration of a body in another frame of reference.